Okay, so today we are going to learn about more advanced techniques to evaluate limits. So in the previous video, we learned about several properties about limits. However, there are some limits that you cannot really evaluate by direct substitution. So let's look at this one. So let's say we have the limit as x approaches 3 of x squared minus x minus 6 and x minus 3. Okay, so this is our limit. Okay, so let's try the method of direct substitution. So this should just be equal to 3 squared minus 3 minus 6 over 3 minus 3. So we have 9, 3 squared is 9, minus 3 is 6, minus 6 is 0, over 3 minus 3 is 0. So you have 0 divided by 0. And this is what is known as an indeterminate form. Indeterminate form. And it's called indeterminate form because you can't really determine a value from this. This fraction is meaningless. This does not mean the limit does not exist. This simply means that the value of the limit cannot be found out at the moment. You cannot determine it from this answer. So we'll have to try a different technique. So let's write this limit. Minus x minus 6 over x minus 3. So you might notice something here. What if you factor the top? So let's do x, as x approaches 3, we're going to factor the top. So because the top one looks kind of factorable. You have 6 as the product. The number should add up to negative x. So you can just do x minus 3 times x plus 2. So by visualizing these factoring patterns, you can determine whether something can be factored or not. So you can see that these two would divide each other out. They would cancel out, leaving with the limit as x approaches 3 of x plus 2. And this one, you can solve a direct substitution. Okay, that's just 3 plus 2, which equals 5. And you can compare these two graphs here, okay, because these two are equal. We just divided something out. However, even though they look the same, they're different because in the top, on the very first function, the rational function, the function is not defined at x equals 3. So this is the top function. It will have a hole. So it looks the same as the graph of x plus 2, except that it's not defined. So that's where the functions are different. Otherwise, the limit as x approaches 3 of this function is the exact same as the limit as x approaches 3 in this function, which means you could safely say that the limit as x approaches 3 of this function is not this, but this, 5. Okay, let's do one more. Let's do a couple more. Okay. So here we have another limit. The limit as x approaches 1, let's do negative 1, of x cubed plus 1 over x plus 1. So if we were to do direct substitution, you would get the indeterminate form. Let's just do this just to see whether it exists. you get the indeterminate form 0 over 0. If you do, one side note, if you do not get a 0 in the top, if you get something like 2 over 0, that means the limit does not exist. Okay? Because the numerator and the denominator approach different values. So the limit does not exist if it's this. Okay? If it's this, then it does not exist. If it's this, then it's indeterminate. And there is possibly another way to figure this out. So just gonna select this, copy it, have another. Let's do the exact same thing here. So if you remember from algebra, there is the sum of cubes. The sum of two cubes, a cubed plus b cubed, is the same as if you were to factor a plus b times a squared minus ab plus b squared. Okay? Which means you could write this as x plus 1 times x squared minus 1 times x is x plus b squared 1 over x plus 1. And again, we can factor this out. And we're left with this function. And if we were to do, now it seems like we can do direct evaluation. The reason why we factor is that we could get rid of that nasty denominator, which makes our limit indeterminate. So now we can easily evaluate. You have negative 1 squared is 1, minus negative 1 is 2, plus 1 is 3. So the limit is 3. Okay, so there is another way. Okay, so let's say we had a limit that sort of looks like this. Limit as x approaches 0 of the square root. So now we're starting to add radicals in here. Square root of x minus 1, or x plus 1 minus 1 over x. Okay? So let's say we had that. So let's try direct substitution. Okay? So if we were to do direct substitution, first we get 0 in the denominator. So you know something's not right. But to see if it can be found, well, square root of 0 plus 1 is 1, minus 1 is 0. So we get 0 over 0. Which means we'll have to take a different approach. So you could use a technique known as rationalizing, in this case, the numerator. Because when we rationalize the numerator, you can rewrite the fraction in a form that eliminates the x in the denominator. So to rationalize any part of a fraction, you would multiply it. You would multiply it by the same thing, except would switch this operation in the middle. So subtraction becomes addition. So square root of x plus 1 plus 1 times square root of x plus 1 plus 1. And the reason why we can do this is that this quantity is just equal to 1. Okay, so if you were to multiply it all out, and the reason why I did different operations, because this looks kind of like a difference of squares expanded out. Like a plus b, a minus b. It sort of looks like that. And you know that's equal to a squared minus b squared. So you get x plus, and square root of x plus 1 squared is just x plus 1, and 1 squared is just 1. So x plus 1 minus 1 times x times the square root of x plus 1 plus 1. So it seems like we made the limit even worse. However, these two go to 0, which means we have just an x in the denominator, so the numerator, which means x is canceled out. So we get 1 over the square root of x plus 1 plus 1, which equals 1 over 0 plus 1 is 1, square root of 1 is 1, plus 1 is 2. So you have 1 half. So that was not bad. This is a valuable technique. And here is again where it shines. So let's do a different one. Different one where we do not have just x in the denominator. So let's do this one. Limit as x approaches 3 of square root of x plus 1, x plus 1 minus 2 over x minus 3. Excuse me. Okay, so we have, if we were to do direct evaluation, you would get the form 0 over 0, because both the numerator, 3 plus 1 is 4, square root of 4 is 2, minus 2 is 0, and the denominator, 3 minus 3 equals 0, are the same value, and they're both 0, which means it's indeterminate. You can't really determine the answer. So what you can do is do a little rationalization. Okay, so that equals the limit as x approaches 3 of square root x plus 1 minus 2 over x minus 3. And through rationalization, we're going to multiply by the opposite operation. We're going to multiply the same thing except with the opposite operation. Okay, so we can get this magical result. We have a minus b times a plus b in the top, which simplifies to x plus 1 minus 2 squared is 4 over, now it's going to be quite messy in the bottom, x plus 1 plus 2. However, the good news is it cancels. X plus 1 minus 4 is x minus 3 over x minus 3 square root of x plus 1 plus 2, which means these two cancel. Okay, and you are left with the limit as x approaches 3 of 1 over the square root of x plus 1 plus 2. And now this looks, you can evaluate it easily. Okay, so that's just 1 over the square root of 3 plus 1 is 4, and the square root of 4 is 2. 1 over 2 plus 2 is 1 over 4. So these are some basic, well, not really basic, but more advanced techniques that help you solve a wider variety of limits.